I want to make a short introduction, but first of all, I want to say that the main goal of this course is to introduce those of you who might be interested to this new direction of research, which, as you will see, is very rich of different kind of problems because it has connections with many fields of mathematics. I want to, before entering into the technical aspects, I want to give you a brief outline of the whole series of lectures. So what I want to do is this. From the philosophical point of view, what we want to do is to answer a very natural question that I think everybody who has had anything to do, even superficially, with quantum mechanics asked himself or herself. So this is the following questions that I have listed have a very long history. And because people ask themselves why, if we want to describe nature, we must use such complicated objects as a non-commuting operator, Hilbert space, and why, from where this very special commutation relation come. There is a very old story about this question, and already the founding fathers of quantum mechanics asked themselves this question. Heisenberg wrote that the mathematical formalism of quantum mechanics is far from intuition. This is in the book Physics and Philosophy. And 50 years later, Nelson invented a kind of paradox by saying first quantization is a mystery and second quantization is a fountain. Now, we will come back on this Nelson sentence, and we will see that this fountain is in fact much more universal than what is usually meant by second quantization. Now, so what I want to say is this. Main conceptual thesis of these lectures, namely, if you combine classical probability with the theory of orthogonal polynomial, you deduce an infinity of possibilities of quantum mechanics, infinitely many. One quantum mechanics for each equivalence class of measures. So, moreover, these extensions are canonical. Canonical means that we do not put anything by hands. We only produce, we only go on deductively. Okay? So more precisely. So in more specifically, what we will do. We will distinguish the various levels. In one dimension, we will prove that every classical random variable x has a canonical is a canonical quantum decomposition, is a sum of three operators which we call creation, preservation, and annihilation, in analogy with quantum mechanics. But they are not the creation, annihilation, and preservation operator of quantum mechanics. Then we will prove that these operators, the cap operators, creation, annihilation, and preservation, satisfy some again, canonical commutation relations. This symbol on the right will be explained today, so I don't anticipate. I only say that it is related to the famous Jacobi sequences of orthogonal polynomials. Okay? I will explain this symbol during the lectures. I just want to give you a broad outline of what we are doing. So, we have canonical commutation relation. There is exactly one class, one Jacobi equivalence class, for which we find back the usual quantum mechanics. And this Jacobi equivalence class, not by chance, is the Gaussian class, which in one dimension is the same class as the Poisson class. And those who know quantum mechanics, in the boson case, they know that in the boson-Fock space you have two fundamental distributions, Poisson and Gauss. It's not by chance that we find them in the same space, the same Fock space. Okay? The point is that the strict positivity of Planck constant, it comes from classical probability. Because the Planck constant in this general framework of quantum theory is simply the variance of the classical random variable. In many dimensions, we have not a characterization, but a characterization of the Heisenberg commutation relation only in terms of Gaussian. We don't know precisely the connection with the Poisson. But we know that the Heisenberg commutation relation are exactly characterizing the Gaussian measures in any finite dimensions. But there are many other classes of measures in finite dimensions, and they obey different commutation relation. If you extrapolate to infinite dimension, you can get a hint of this fact that many attempts have been done to create a non-trivial quantum field theory, interacting. Now, these attempts in the past 50 years have essentially failed, even if excellent mathematicians were devoting a lot of their life to it. I think that this can give a kind of theoretical hint why this happened. Because everybody was trying to fit the class, the Heisenberg commutation relation. Because for all these years, the quantum mechanics was the Heisenberg commutation relation. So they were trying to fit the Heisenberg commutation relation within a measure which is a norm-product measure. But we know that from the theorem that I mentioned, if you have the commutation relation, you must have a Gaussian situation. And the Gaussian measure with a linear transformation in the base space is reduced to a product measure. So non-interactive. So the message will be this. If we want to go to deal with really interacting non-linear theories, we have to change the Heisenberg commutation relations and to use the canonical probabilistic ones that I will describe. Okay. A very short historical outline of this problem. There were four crucial moments in this point. The first was, in fact, a corollary of a paper which was devoted to physics, namely the discovery that there is a very natural object which is called interacting Fock space, which generalizes Fock space. What we will study in orthogonal polynomial will be particular interacting Fock space. And one of the most difficult problems has been for many years to characterize the orthogonal polynomial within the family of interacting Fock space. I don't give now the precise definition, but intuitively, what is an interacting Fock space? Intuitively, interacting Fock space is the most general Hilbert space or pre-Hilbert space where you can define creation and annihilation, and they are adjoint of each other. It seems a very small requirement, but it's very rigid. it imposed a lot of constraints. Okay? So this was the first interacting Fock space. A few years after the discovery of interacting Fock space, we discovered with Bozzecco that if we restrict to the simplest possible situation, the interacting Fock space over the complex numbers, so essentially one variable, 1 degree of freedom, then this 1 degree of freedom interacting Fock space are in one-to-one correspondence, even isomorphic in the category sense, with the theory of orthogonal polynomial in one variable. Okay? And then the third phase transition was to go from one variable to more than one. This was very difficult. It took many years. The last paper I have mentioned, it just appeared in the first issue of Ida Copy of this year. And during my lectures, I will try to, you will understand why the transition from one variable to multivariable.
Could you just show the previous reference, that interacting Fock space and Gaussian distributions? Like the previous reference that was there of you.
No, Fock space and Gaussian.
He wants the
Not
previous
in.
page. Previous,
I don't understand the question.
previous page.
Yeah, this and Gaussianization of. Okay.
Still previous.
No, it's okay. I just needed this reference. You see.
But I will leave you this slide, so you will have, and you can take all the references. Yes. So, in the infinite dimensional case, is now just beginning. There is an unpublished paper. We have a beginning, but there is another phase transition of difficulty. And I will try in my last lecture, or lectures, it depends on the time, to explain what is the additional difficulty that comes here. So, I will not speak of interacting Fock space, only I will give the definition because we will need, but I will not discuss in much details. So, my lectures will be made of 3 parts. The first part of lectures is devoted to a single random variable. This is the simplest possible situation, but don't under-evaluate it, because if you understand very well it, you have a very good help to understand the multidimensional case, okay? So, because I will try to develop all problems that are mainly open in the multidimensional case, still open, but we understand them in the one-dimensional case. And so I will do a detailed description of these problems as an introduction to the open problems, okay? So, the second part, I will deal with finitely many degrees of freedom. And you see, in the first part, one polynomial with one variable corresponds to quantum system with 1 degree of freedom. In the second part, I deal with polynomial with many variables, and they correspond to quantum system with a finite degrees of freedom. Finally, in the third part, I deal with, so in a probability language, this is real valued random variable. This is vector valued real random variable, that is random variable with values in a real vector space of finite dimension. And in the last, you have random variable with values in an infinite dimensional vector space, and these are the fields. And you go to quantum, they become quantum fields. So now, let me begin. You can take up the screen. I can now begin to give to write on the lecture.
Shut down the computer.
Because I shut down I simply cut the projection. Can I simply take it off? one-dimensional vector space with a basis. The basis in a one-dimensional vector space is simply a single vector which is non-zero. Once we have this, we identify the vector space V with the basis with the real times E. That is, the introduction of a basis is equivalent to introduce the coordinate functions. I am doing in one dimension, but you should think of R as a manifold. So you understand what does it mean to introduce coordinates. Because one of the open problems will be to extend this to manifolds. And so I use a language which is useless in one dimension, but which can help your intuition to prepare the ground for manifold. So to put the coordinate on R is equivalent to define the coordinate function. Because once we have the basis, every vector is a multiple of the single vector of the basis, and so we have the coordinate function, which is a real valued function, x, e, y. Okay? Now, so once we have the coordinate function, once you have the coordinate function, we can form the monomials, because they are functions. It's defined pointwise. So we can define pointwise multiplication, addition, and complex conjugation. So I will consider the monomials, and more generally, I will define P, which in fact obviously depends on V, as the algebra of polynomial, the complex polynomial algebras, complex polynomial algebra, in the coordinate that we have fixed. So essentially the elements of this will be functions of this form. Aj times x e1 to the power n. Well, we can put j because it's a finite sum, for example, j from 1 to some capital N. Capital N is arbitrary, but the important point is that while the vector space is real, the numbers, the polynomials that we consider are complex. Okay? Now, once we have the polynomial algebra, see, since every polynomial is a linear combination of monomial, we have the following direct sum decomposition, which is simply, I take is complex times the unique in one dimension. You have a unique monomial of degree n. That is why there is a big difference between 1 and 2. Because as soon as you go to 2 dimensions, the monomials of degree n are of order n times n minus 1. There is a combinatorial formula that I will show you. So the dimension of the space of monomials of degree n grows with n. In fact, in dimension d, you show that it grows like n to the power d minus 1. So that is why 1 is critical dimension. Okay? So this is called the monomial gradation. And this I put dot to mean that this is a direct sum in the sense of vector spaces. And I will denote for future use, this is what we call Pn. Of course, the Pn are vector spaces. P is a star algebra for the multiplication, for the pointwise operation of addition, multiplication, and complex conjugation. So P is a star algebra. And Pn, P0n are not a star algebra, they are simple vector spaces. Now, an important point is that this star algebra is a real structure, because every polynomial I can separate the Aj, I can separate the real and imaginary part. So I have a real structure of this algebra that I will denote like this. And the sum is direct, but not ortho. Of course, now it makes no sense to speak of ortho. And this decomposition is transported to the monomial gradation. It's transported to the monomial gradation. Now is an important point. Well, this I gave the, I don't know if to give the proof or not, because it's already almost half an hour. But there is an important, crucial point that is this. One dimension is very special. You see, you have a star algebra. Remember, we will be interested if I gave a probability measure on R, on the real line. Infinity means infinity means the space of probability measures with moments, finite moments of any order. Okay? So for me, probability measure from now on, when I speak of probability measure, I always assume that there are moments of any order. Given a probability measure, I can define a state of the polynomials and a linear function of the polynomial, which is the integral. Because these are the polynomial in the coordinate, and so the coordinate is defined on the real one-dimensional space identified to R, so it makes sense to speak of integral of dx mu dx. This, now we come to the subtle point. This mu, this integral, that I use the same symbol you see for mu as a state, as a linear functional, that is the integral, and mu